Okay, so I hope this is working. I'm not sure. I get a little delay in my viewing of it compared to what I'm actually doing. So if you can, someone message either via the chat or on Edsby messages, um, even through email, and let me know if you can hear me fine, because I'm not sure if you can or not. But what I'm going to do is just kind of get started here with a little bit of review of the concept of a parabola just to quickly go over that. And then if you guys have questions, again, you can try send some through the YouTube chat. You do need a YouTube or Google account with that, so you may need to make one, even if you want to just make a fake one. Or you can message me through Edsby, and I have my email open too, so you can send me something through there. But we'll start with a little bit of just the idea of a parabola. I'm actually going to, I think I'll actually use Desmos for this. So I'm going to switch over to Desmos here. Just give me a second. Okay, so here, looking at Desmos, so just the concept here that we want to do is look at the idea of a parabola. So we're moving away from lines, and these parabolas have equations that are y equals ax squared, move my mouse here, plus bx plus c. This is our standard kind of format for it. So a, b, and c are all numbers. A, the only restriction is it can't be 0, because if I set it here to 0, I get a line, and we don't want lines. So a has to be anything but 0. Traditionally, it's just x squared. So I'll set b and c to 0. So this is our kind of traditional looking parabola here on the screen. It goes over 1 unit. So these are all half units here. So it goes over 1 unit, up 1 unit, and then continues over in each of these of 2 squared, 3 squared right here at 9. So each of these different points, and I can kind of click on there too. So this shape here, and you can use this site Desmos. Again, it works on your phone, works on your as well. There's an app there, or you can just go to the website. You slide these around, you can see some of the modifications of it. So as I move the a value, and so that's that value in front of the x, it makes the graph get skinnier. Or if I get less than 1, it starts getting wider. And then as I pop it over to the negative, it actually flips the graph and mirrors it underneath the horizontal axis. In the case of the b value, I'll use a wide one here just to fit on the screen. In the case of the b value, it's going to move the graph around and switch it around. We don't really work with the b value per se in changing the standard form here. When we look at some of the other forms, we do. And in the case of the c value, that one, I didn't really note that in your notes, but the c value in this case does represent the y-axis, the y-intercept. So that's where the graph actually hits the y-intercept. So even though I'm changing the b value, I'm changing the a value, that y-intercept is always staying the same. So that's the kind of key notes on the graph. Now, with moving around with it, but the graph itself has a couple key features that we need to know of. The one key is down here, this point where the graph changes direction. So it's coming down and then it switches to going up. That point where it switches, that point is called the vertex. And it's important to use when we do it. So we have the vertex, and we'll write this out in a quick little note here shortly. We also have the x-intercepts. You can have 2 x-intercepts in the case of a parabola, or if we just kind of move this around here, we could have no x-intercepts like this one here, or you could have, and I'll try and get there, it's going to be tough. Number in there, 7. about right there, about 1.78. So here it just kind of touches the x-axis and bounces off, so we could have the one x-intercept as well, depending on how the graph looks. There'll always be a y-intercept though. Whatever case, it's always going to cross over the y-axis. So if we kind of flip over to the note again, note paper here, I'm going to draw a quick little sketch of a parabola. Just have some xy axes here, really quick. And so a parabola is going to be this U-shaped graph. Graph itself, this U-shape, it's always a parabola. Parabola. Let's see if I can get that focused a little better. There we go. Sometimes we just call it a quadratic. So it's a quadratic graph. And then we have our key points here, the x-intercepts, vertex, y-intercept, and there's a couple others. So first off, this is the vertex. We often label it as HK, which is in the next note there. The x-intercepts, and then the y-intercept. On top of those, there's another key point. There's kind of line actually. I'm going to draw another quick one here. So a key line, and if you remember elementary school, I used to have these red mirrors, at least I did. We'd put them on the graph or on an image in the paper, and it would actually mirror that image on either side of that line. Now in my case, my drawing, not the best, but this line here, called the axis of symmetry, is where you could see that graph mirrored on either side. If you were to put one of those little red mirrors on there. So each point from here to here is the same distance apart. Again, it doesn't look like that on my graph, but my drawing is not the best. So that axis of symmetry is an equation, x equals, and then it'll be the h, or the h value of the vertex. So those are some of the key kind of features in and around parabolas. If anybody has any questions in regards to any of the textbook questions that you want me to go over specifically, please let me know. Again, got email up, Edsby, and on the YouTube chat here. Otherwise, I'm just going to pick a couple just to take a look at that I think are good ones that'll show you how to use Desmos or how to do some sketching quickly with the graphs here. And so I'll start just with number 1 for now. And in question number 1, it says to, and I'll switch that up on the screen here. There we go. So up on the screen there, you should see question number 1. And what question number 1 has here, and this is from section 4.2. The table shows the path of a ball where x is the horizontal distance in meters and h is the height in meters above the ground. So this is an often situation that we use. When you throw something through the air, it's going to kind of follow this parabolic path. Throw a football, a baseball, kick a soccer ball, anything like that, it's going to have that kind of path to it when you're measuring the distance and height of it. So we want to just sketch a graph. So when we're asked to sketch a graph, we don't have to necessarily put all nice, neat, perfect lines and points. In the terms of sketching, we just want to get a rough approximation that'll get us some information in regards to the graph and just kind of visualize the situation. So that's our question there. I'm going to switch over to the page here, and now we'll take a look at that question. So that's number one. I'm just going to kind of switch back and forth here a little bit, but there's our table of values. So it's the x values go from 0 to 8, and then the h values, the height values, go from 1 all the way back to 1. And so if I start drawing that, I'm going to just draw a graph like this. I don't need negative values in this case because our object is traveling only in positive height and positive distance. If we had negatives in there, negative height would be going underground in this situation, and negative distance would be traveling behind us. This is my x, this is my height, and so we're about 1 to 8. So 0, that's about 8, about 4. Just a quick little scale here, and then on my h-axis, we're getting up to 17. So I'm just going to put about 18 on there, because then I can divide that up 9. That'd be about 4.5, so on. So we can kind of get a rough estimate of our graph here. And so now I'm just going to roughly put the points. I'm looking at the table, and I'm going to look for some key values. So when x is 0, I have a height of 1. So actually starting 1, and I believe that was in meters. Yeah, 1 meter off the ground, and it's actually finishing at 8, 1 meter off the ground. And because parabolas are symmetrical, each of these sets of points you can see have a mirrored point. If I transition back here, each of these points is mirrored. So we have, let me switch over, 0 and 1, and 8 and 1. We have 1 and 8, 7 and 8, 2 and 13, 6 and 13. So parabolas will have this. We might not always have all those points listed out for us, but there'll always be a mirrored point in the equation of a parabola. So in this case here, all these points are mirrored. So I can kind of use that to kind of roughly estimate without drawing every single point down here. So I'm just going to switch back again. And that maximum height was at 4 and 17. I put a point there. And just a couple other quick ones would have been 2 and 13. So if that's 9, about right here, 2 and 13. And then that would also mean that 6 and 13 there. And I'm kind of just picking these second points sometimes. I'm just thinking of them in terms of being symmetrical. So I'm going to try and connect the dots. And these aren't straight lines, so don't use a ruler and connect these. That's not the right way to do it. These are not a line graph. Are a curve. Should follow a smooth curve. Best you can draw. So there's my parabola. So there's a sketch. That's a little more detailed sketch, but I wanted to kind of go over a few of those concepts with you. The key idea here is that we're getting really the start, the end, and the vertex. Those are the important points in this situation that'll help us with understanding some of the questions, such as question number 2, or 1B, sorry, that says, describe the flight path of the ball. Identify the axis of symmetry and the vertex. So the flight path of the ball might be described something like ball starts 1 meter off the ground, travels up to 17 meters, and stops 1 meter off the ground. And now that describes the height portion of our graph, but it doesn't describe the vertical travel. So we're going to put that in too. Something like over 8 meters along the ground would describe that. So we want to make sure we're describing both our vertical and our horizontal movements here. And it had also said to identify the axis of symmetry and the vertex. Well, the axis of symmetry is that line that cuts that graph in half in a symmetrical manner. So here we have a symmetrical graph. I can kind of put that ruler on top and I'll line that up. There we go. And so our graph is mirrored on either side of my ruler. So that's our axis of symmetry. And so I'll just kind of dash a line through that. So this is my axis of symmetry. And it occurs at x equals 4. So the axis of symmetry occurs at x equals 4. And the vertex is this point right here. Vertex occurs at the point 4 and 17. And so that would give us the answer to 2. Give us a description of the flight path, identify the axis of symmetry, and vertex. In part C, it had asked for the maximum height the ball reached. Well, the maximum height the ball reached is the other portion of the vertex. So the axis of symmetry is the x value of the vertex. This portion of the vertex be the maximum, or in the case of a graph opening the other way, a minimum height or distance or something. So in our case, the max height is 17. And now the last bit asks us to verify that the equation h equals negative x squared plus 8x plus 1 can be used to model this path. So we want to see if this can model our flight path. Well, just quickly looking at it, a couple things stick out that help me think yes, it does. The value of 1 here at the end, because this is in that standard form, the value of 1 at the end, that's our y-intercept. And our y-intercept was at 1. So that works. This negative sign, when there's a negative in front of the x squared portion, negative number, in this case negative 1, that tells us that the graph is going to open downwards like this. So it's going to be the upside down U. So right there I'm thinking, yeah, this probably works. And then to test out, so I know this point's good, I'm going to test out one more point, and I'm actually going to test out the vertex. So I'm going to sub these two values, 4 and 17, into this equation. And it's going to help me verify that this is going to work. So 17 would be our height, and when this height is 17, the x value is 4. So just fill that in. And now I'm going to calculate this right side, and if the left side equals the right side, then this is a valid point, this equation. So 4 squared. Notice I put the 4 in brackets here. Good practice. 4 squared, 16. This makes it a negative 16. So it's not negative 4 squared, it's 4 squared with the negative sign separately. So negative of 4 squared, which is 16. 8 times 4 is 32 plus 1. And if I do negative 16 plus 32, it's going to give me 16. 16 plus 1 is 17. 17 equals 17. So this is a good point. So I know 1 and 0 is a good point. 4 and 17 is a good point. I could test a couple more points if I wanted to, but I'm going to say this is going to be a verified in that this equation does model the light path of the ball. And again, if you guys have any specific questions you want me to look at, send me a message. Let me know. Otherwise, the other one I wanted to look at would be the finite differences as a last question here. And so I'm going to switch over and we'll take a look at for 3A. So we're going to look at 3A. We're going to determine whether this is linear, quadratic, or neither. And so what we're going to do is we're going to make an additional column or two, depending on how many we need, at the edge of this to see if it is linear, quadratic, or neither. And so I have x is 0, 1, 2, 3, and 4. Y, it was 4, 5, 6, 7, and 8. And so if the first differences are the same, then this will be linear. If they're not, we can try the second differences and see if it is quadratic. So I'll take a look here. There is no value for the first one. We're always subtracting y value minus its previous one, so there's no previous value here. So here we have 5 minus 4. 5 minus 4 is equal to 1. The next one is 6 minus 5, which is equal to 1. And then 7 minus 6 equals 1. And number 8 minus 7 equals 1. And I'm getting a couple questions, so we're going to take a look at number 5 afterwards as well, and number 9. So we'll look at 5 and 9 as well. But we'll finish up this one here. So looking here, first differences are the same. So since the first differences are the same, we have a linear equation. And now if they weren't the same, all we'd do is just make a second column, and then we wouldn't do the first two, and we'd do this number minus this number, this minus that number. And so we can just subtract through those and determine whether or not we have a linear quadratic equation. If the second differences and the first differences aren't the same, then that next situation is that we have a other type of polynomial equation. Could be a cubic, could be a quartic, quintic, or any degree beyond that. Could be just a random graph as well, where there's just a scatter plot kind of idea. All right, so we got a request for number 5 and number 6. Switch over here, or sorry, number 5 and number 9. So number 5. That up on my screen. Number 5 here. We're looking at the Humber River Pedestrian Bridge in Toronto. It has the equation h equals negative 1 over 144 x squared plus 5 over 6 x, where x is the horizontal distance in meters from one end and h is the height in meters from the water. So we're going to graph this with or without technology. I'm going to say you want to probably use technology on this one. This is a you're going to get some interesting numbers. You can do a quick sketch of it, but in my recommendation, I would actually do this using Desmos. So I'm actually going to flip over to Desmos here, and we will make a copy equation. Just clear off what I have here. And we're going to add a new graph. And so the equation was, I'm going to switch the h to y, but y equals negative 1 divided by 144 x to the power of 2. If you're having trouble with this, you can use the keypad down below here, and you can add your squareds and things like that. I'm just using some of the shortcut keys to do this. Plus 5 over 6 x. So there's our equation. I'm actually going to set my view here. So I'm going to start at 0 on the x-axis and test out. 50 doesn't seem to be big enough. There we go, 120, 0 to 120. So I will set that from about 0 to 120. And I'm going to use the same scale on the y-axis just to kind of give it a square grid. So if we have a square grid, each of these grid pixels is not really that square on my screen. It's I'm going to zoom out a touch then. So this is the actual portion of the graph that we would use from here at 0, 0 to 120 and 0. In between is the actual bridge. Anything after that, this wouldn't exist in real life. This again is the height above the water. Well, that's at the water. That's at the water. The rest of this wouldn't be a point of putting the bridge underwater. So there's our graph of it. And so there's a technology version. Again, you could pick some values and try and do this by hand, but it's going to just take a lot of extra work to do that. And then it says, what is the height of the bridge? 12 meters horizontally from one end. It doesn't matter which end you pick because this is a symmetrical graph. So we can go in here and use this, try and approximate it. And so it's going to be about, there we go, 12 and 9. So the height's going to be 9. So you can use this to find the height as one way. The other way is to actually sub the value into the equation. So we want to know the height 12 meters from the end. So we could actually, and I'll switch over. Sorry, 5b, the height from one end, 12 meters from one end. So we just take the equation h equals negative 1 over 144 times 12 squared plus 5 over 6 times 12. So we use that equation there, and we just calculate it out. 12 squared is going to give me 144, so that's going to be 144 over 144, so negative 1 plus, and then 5 over 6 is going to give me 60 over 6, so 10, and then h equals 9, and that's that same value that we got on the graph on Desmos. You could also use the number 108. That would be 12 meters away from the far end of the bridge. Both of those will be the same height. How wide is the bridge at the base? In this case, flipping back over, we want to look at our so I can see it too, our x axes and our zeros. So from one zero to the other, the distance along the bottom here is 120. We start at 0 and we go over to 120. So the part C, which is how wide is the base of the bridge, or the bridge at its base, that's 120 meters in this case. In part D, D asks what is the maximum height of the bridge and at what horizontal distance does it reach that height. This is asking you for the vertex. So whenever you're looking for the maximum height or the minimum height of something, the maximum or minimum value of a quadratic is always going to be the vertex. So our vertex is right here at 60 and 25. And so maximum height is 60, it occurs at 25 meters from the end. Or sorry, the maximum height is 25, the y value, and it occurs 60 meters from one end. My mistake. So 25 is the maximum height, 60 is the distance across. And then the last part there says to identify the axis of symmetry. Well, in this case, the axis of symmetry is going to be at the x value of the vertex, and our vertex x value is 60. So the axis of symmetry is x equals 60. So that there, in blue, is our axis of symmetry for this graph. So I hope that helps out with number 5. And then there was a request for number 9, I believe it was. Yeah, number 9. All right, so number 9. I'm going to switch over to paper here. And refresh that. Okay. So, may have missed a little bit there when I did the calculation. Let me flip that back. I didn't realize the camera had frozen on me, but for 5b, that's the calculation where I just subbed in the values in and calculated 5b. But we're looking at number 9 here. Now, so number 9 is asking us about the path of a rocket that we're firing. Let me pop it up here. Number 9, the path of a rocket fired on at a Canada Day firework display is given by the equation h equals negative 4.9 t squared plus 19.6 t plus 0.4, where h is the height in meters of the rocket above the ground and t is the time in seconds. We want to make a table of values for this. So all we're doing is making a little t-chart. So we have our t and h values going 0, 1, 2, 3, 4. And so what we want to do in each case to actually finish that table is we're going to sub in these values into the equation, which is h equals negative 4.9 t squared plus 19.6 t plus 0.4. So we just take each of these values and replace the t in there. So in the first case, it's going to be, just kind of right off the side here, negative 4.9 times 0 squared plus 19.6 times 0 plus 0.4. Our 2 multiplied by 0 is going to make those both 0, and so we're just going to end up with 0.4 as our first h value. And then we just go through each subsequent value, subbing in. Plug those in, and then we do a little bit of calculation. So I have negative, and I'm getting 15.1. And I'm just going to quickly calculate the rest of them here. $20. $15.1. And now, knowing that a parabola is going to be symmetrical, and we've gone down 1 point here, the last value that should be 0.4. So that would be our table of values there. I cheated a little bit, knowing the layout of a parabola, and use that to help me determine the values of everything. All right, so now if I look at the next part of the question, then the next part is asking us, make a table of first and second differences, and what conclusion can you make? So I'm just going to need to recopy that because I put that in the way. So I got 0, 1, 3, and 4, 0.4, 15.1, 20, 15.1, and 0.4. That's my h, that's my t. So if I make a table of differences now for these, there, I've just recopied them quickly, and my first differences, can't do the first box, so I do 15.1 minus 0.4, and I'm going to get 14.7. Then I do 20 minus 15.1, and I'm going to get 4.9. And then I'm going to do 15.1 minus 20 and get negative 4.9. Notice it's negative because it's not just the big one minus the small one, it's always the next number here, this number minus the previous. And then lastly, 0.4 minus 15.1, which is going to give me negative 14.7. So there are my first differences. Those are not the same. So right away I know this is not going to be a line. This rocket does not travel in a straight line. It must be curving somewhere along the way. So I'm going to do a second set of differences here. Can't do the first one, can't do this one, but now I can subtract 14.7 from 4.9. So 4.9 minus 14.7 is negative 9.8. And then negative 4.9 minus 4.9 is going to be negative 9.8. And then negative 14.7 minus negative 4.9 is going to be negative 9.8. Those are all the same. So what conclusion can you make? This firework is follows a parabola. Now this is actually a situation where they actually used a real world type of equation, because this second difference of 9.8 and that negative 4.9 t squared at the start of the equation, these actually are based on the acceleration of objects due to gravity. The negative 9.8 is how fast something accelerates when you drop it. So any object that you grab and drop near the surface of the Earth, throw a rock out your window, and it's going to accelerate towards the ground at the speed of negative 9.8 meters per second. So this actually meters per second squared. Acceleration is a second squared. But this is actually the number based on that. So this is a realistic type of question. The next part says draw a graph of table of values from part A. So you can use the table of values, or you can use graphing technology. If we were to use a table of values, we could just do a quick little x, y axes. Again, I don't need the negatives in this case, so just do a quick sketch like this. And 0, that's about 0.4. Actually, it's a really bad start for that graph. Here, let's not start there. Say this whole thing is, what's the max height there? 20. 20. 2. 4. My time. My height 20. That'd be about 10. So if I'm going to quickly graph this, 0.4 and 0 is going to be about here. Here. And then 1 and 15.1. So that's about here-ish. 2 and 20. Graph's going to look something like this. I'm actually going to finish it off there and have it hit the ground just past 4. In the case of a firework, it might have actually exploded at the top there, but this is our situation. Or sorry, a rocket. This is a rocket at a fireworks display. This isn't actually a firework. So there's a quick sketch of it. Or we could use graphing technology, so we could just switch over here to Desmos, and you could just pop in that equation. Showing the screen. I'm showing the screen. Okay. Y equals negative 4.9 x instead of t to the power of 2 plus here 19.6 x plus 0.4. So this here is a graph of that. The rocket goes up, rocket goes down. This is not the flight path of the rocket. This is just the horizontal, or this isn't the horizontal, this is the time. So this is just measuring the vertical height of the rocket at any given time. So this point here, 2 and 20, is at 2 seconds, it's 20 meters high, not 2 meters over. So the last question there is, how high was the rocket off the ground when it was set off? Well, it's at 0.4 meters, or even looking at our table, it was set off at 0 seconds, so it was 0.4 meters or 40 centimeters off the ground. Alrighty, so if there's no more questions, then I think we'll wrap this up for today. Feel free to let me know what you thought, if there's something we could do better next time. We'll take a look at early next week to do the next little video chat here. Okay. You guys all have a good day.